So, in the previous problem you have seen that this is nothing but a jugglery of the boundary conditions, the original equations remaining similar. Now, in the two cases we have seen that outer cylinder was rotating and inner cylinder was fixed, right, and that can give you a way of finding out the velocity profile, also the way of finding out the viscosity. In many instruments there we had earlier said that Brookfield viscometer uses a similar situation. Now, if the condition is a little different, that if instead of outer cylinder rotating and inner one fixed, and we played with the radii, right, we made outer cylinder one radii, inner cylinder another radii, of course the velocity expression that becomes different, right. So, if we do the other one, that the outer one is fixed and the inner one is rotating, right. In that case, if we take the former equation, that is the first one like that, then let us see how it happens. Okay. So, here the same problem, if an incompressible fluid is flowing between two vertical coaxial cylinders and the inner one is rotating with an angular velocity omega, determine the velocity for the tangential laminar flow, right. Now, the inner one is rotating and the outer one is fixed. So, this outer cylinder is stationary and inner one is fixed, rotating rather with an angular velocity of omega, right, and we kept that r and kr as the first case, that this is r and this is kr, right. If we keep them like that, then we can say that the problem can be defined like this. We have one inner cylinder, we have one outer cylinder, this is the center, right. This outer cylinder is fixed and the inner cylinder is rotating with an angular velocity of omega, right, and we gave as earlier the same, this is r and this is kr, that is k is multiple more than 1, right. So, that kr is greater than r, right. So, if we take this problem and solve, so like the previous one or in earlier cases, if we use the Navier Stokeâ equations, right. So, we can write, and here also we have number 1 steady state, number 2 your laminar flow, number 3 is incompressible fluid. And of course, others like flow is fully developed, there is no end effect, all these are also there, right. So, we can write from the Navier Stokeâ equation, right, the same as earlier, like from the given problem by physical understanding of the problem, we can write Vr is equals to Vz is equals to 0 and del V theta del theta is also 0. That means this is not changing with the theta, right. So, if that be true, then this is the understanding of the problem we can write. And from the Navier Stokes equation, we can write rho v theta square by r. This is equals to minus del p del r, right. This was our first equation. Second equation, we can write that 0 is equals to del r of 1 by r del r of r v theta, right. So, this was our second equation, and the third equation we can write 0 is equals to minus del p del z plus rho g z, right. Now, from these three equations, since we need the solution of v theta, so this equation if we take, then we can lead to the solution, and that equation if we rewrite, we can write del r of 1 by r del r of r v theta, this is equals to 0, right. And we also wrote that on first integration, we write that on first integration we write 1 by r del r of r v theta, right. This is equals to a. On simplification, we write del r of r v theta is equals to ar, right. On second integration, we write integrating, again integrating. On second integration, we can write that r v theta is equals to a r square by 2 plus b, or v theta is equals to a r square, or r square goes out, a by 2 r plus b by r. So, again up to this, that is the equation A, the solutions remain identical. Where we are seeing the changes are in the boundary conditions, because our boundaries are changing, right, either with the diameter or radii or with the condition of physical condition of the problem, they are changing. So, boundary conditions are changing. So, this is again nothing but a change of the boundary condition, right. So, we write the boundary condition 1. What is given? We have been given, said that the inner cylinder is rotating and the outer cylinder is fixed, right. So, we have at r is equals to r and at r is equals to kr two different conditions. So, what are those two different conditions? Boundary 1, if we write at r is equals to kr, v theta is equals to 0, because this outer cylinder is fixed, right, outer cylinder is fixed. So, v theta is equals to 0 at r is equals to kr, right. So, at r is equals to kr, v theta is equals to 0, this is boundary 1, and boundary 2 is r is equals to, sorry, that is v theta is omega r, v theta is omega r at r is equals to, sorry, at r is equals to capital R, right. So, these are the two boundaries we have to substitute, right. These are the two boundaries we have to substitute, and when we are substituting them, then we see that the first one at r is equals to kr, v theta is equals to 0. If we put this in equation 1 or A, if we put v theta is equals to 0 at r is equals to kr, we get what? So, v theta is 0, r is kr, so it is a k r by 2 plus b by k r, right. So, this is say equation B, and second equation is v theta is omega r at r is equals to kr. So, we write here again from equation A, we get that v theta is equals to omega r, right, at r is equals to capital R. So, it is a r divided by 2 plus b by r, right. So, again by substituting 1, this is C. So, by substituting 1, that is B is, from B we can write B by K R is equals to minus A K R by 2, or we can write B by R is equals to minus A K square R by 2. So, if we substitute this B by R, right, if we substitute this B by R into C, we can write from equation C, we can write that omega R is equals to A R by 2 plus B by R has become minus plus minus A K square R by 2, right, or we can write omega R is equals to A R by 2 minus A K square R by 2, right. So, this on simplification we can write A if we take out, or A R also if we take out, then we can write this is 1 by 2 minus this is K square by 2 is equals to A R into 1 minus K square by 2, right. So, we can write from there that omega R is equals to A R into 1 minus K square by 2, or A is equals to omega or 2 omega by 1 minus k square. So, if A is equals to 2 omega 1 minus k square, so this is relation E. We can write from the other one relation B from equation D. We can write B by R is equals to minus A k square R by 2, right, is equals to, if we write k value, so it is A B by R is equals to A is minus then 2 omega by 1 minus k square, this is 1 into k square R by 2, right. So, B becomes equals to minus 2 omega k square, this R into R goes R square by 2 into 1 minus k square, right. So, if we substitute A and B in the original equation, that is either B or C, right. So, if we substitute them in B, we had 0 is equals to A k R by 2 plus B by k R, right. So, this is equals to value of A we know, this is 2 omega by 1 minus k square, right, and k R by 2 plus, right, this is minus, we are substituting B by k R, right. So, this is 1 by k R we will write afterwards. So, B is equals to minus 2 omega k square R square divided by 2 into 1 minus k square. So, this of course 2 goes out. So, we could write it minus omega k square R square by 1 minus k square. This is for B. So, we substitute this 2 and we can rewrite this is equals to 2 omega k R. So, this 2 and this 2 goes out. So, this 2 is also not there. So, 1 minus k square, right, omega k R by 1 minus k square, this is minus. So, this is omega k square R square by 1 minus k square, right. So, if that is true, we can write this substitution we should have done not here at, we should have done at this equation A. From equation A, sorry, this should not have been, otherwise V theta is not coming. V theta is A R by 2 plus V by R, right. So, here we are substituting A as 2 omega by 1 minus k square into 2. So, this 2 goes out, this is here by 2 plus B or 1 by R into minus 2 omega k square R square divided by 2, this 2 of course goes out. So, 1 minus k square, right. So, we can write now that omega by 1 minus k square minus 1 by r, right, a r by 2. So, it was 2 omega into r, right. So, omega r by 1 minus k square, 1 by r minus, and this is omega k square r square by 1 minus k square, right. So, this is the v theta, which of course we can further simplify as omega. If we take common, then 1 r by 1 minus k square minus omega is out. So, k square r square divided by r into 1 minus k square, right. So, this is the solution, right. So, if we look at, then this should be the solution. Let us look into the final solution which we have gotten on the same way, on the same thing we have done. You see, boundary condition was v theta is equals to 0, with here v theta is equals to 0 at r is equals to k r, right, and v theta is omega r at r is equals to r, right. V theta is equals to omega r at r is equals to r. This was our v theta is 0 at r is equals to k r, and v theta is equals to omega r at r is equals to r, right. So, if we do that, we got a is equals to, you see, we got a is equals to, here we got a is equals to 2 omega by 1 minus k square, right, and b we got is equals to minus omega k r square, omega k square r square by 1 minus k square. That is true, and we got v theta is equals to ultimately this omega divided by omega, okay, omega we can also write in this form. This is equals to omega by k square minus 1. If we take common from here, then k square minus 1, so 1 negative we have taken inside, right. So, that becomes equals to this into, then first term is this one. So, k r square divided by this r remains there, right, and this r then goes there minus r. So, omega by k square minus 1 into k square k r whole square by r minus r. This form and this form are same. So, we can say we have done the right thing. Only the thing which is required, which you need to do here in between, if you look at the solutions, the same solution original which we had started with, we have done up to this the same, right. Then we have changed the boundary, right. So, boundary was originally here v theta is 0 at r is equals to r, and v theta is equals to k r, omega k r at r is equals to k r. Here it is getting changed that v theta is 0 at r is equals to k r, and v theta is equals to omega r at r is equals to capital R. So, this change we have to do, and then as we have shown the solutions here. So, in that way, if we go and solve, I hope you will get the same. Please do the required changes. Please do the required changes in in the slides. Okay, let us also, since we can do it, let us look into this and do that. Boundary condition was V theta is equals to 0 at r is equals to kr, at r is equals to kr, and we can write V theta is equals to omega r at r is equals to r, right. In our new system, here as we have seen, this is omega r and kr, right. So, at r is equals to r, this V theta is equals to 0, this is fixed. So, at r is equals to r, this is V theta is omega r, and at r is equals to kr, V theta is 0. At r is equals to kr, V theta is equals to 0, and this. Now, if we substitute them, then we can write that in the first one 0 is equals to here, right. 0 is equals to a into r by 2 plus b by r. This we have V theta equals to 0 at r is equals to kr. Oh, then this should be 0 is equals to a kr by 2, and this is b by kr, right. And in the second case, omega r is equals to a r by 2 and b by r, right. So, from there the same, this of course repeat. So, hopefully we can delete this. Okay. So, from there we, on simplification, we don't write all these because we have shown you there. We can write simply that what is A. So, A has come 2 omega by 1 minus k square, 2 omega by 1 minus k square. This is 1 minus k square, right. So, we put here as square 1 minus k square, right, and b is equals to, but is also required, and b is equals to, we have obtained here, as you see, that b was this minus omega k square minus omega into k into r whole square. That is much easier and better, k into omega square, right, and this divided by it was 1 minus k square, right, 1 minus k square, right. So, that k square is this, one minus k square yeah. So, if that be true, then the final equation which we got for V theta was this. V theta was omega by k square minus 1 omega by k square minus 1 k square minus 1 right times, if we take this, times k r square by r k r square by r minus r, right. So, this was our solution. So, we got it. So, we have corrected also. So, as we requested you in the previous class, in the previous problem that we have done on the paper, but corresponding slides were not properly corrected, and we requested you that if you go into that slide, get that thing corrected, and because we have done on the paper, here we have done both on the paper as well as on the slide. So, this is the final V theta expression, that V theta is equals to omega by k square minus 1 into k r square by 2 by r square by r minus r. Okay. So, hopefully we have seen it, and that is the final. Thank you.